Hello, everybody. Can everybody hear me okay? Are we good? All right. Looks like we're a couple minutes past, so I think we can go ahead and get started. Welcome to our session on capturing the dynamics of hydrologic systems through consumptive use measurements. My name is Garsha Amidi Abraham. I'm not Matt Bromley. Matt was unable to make the conference, I think, due to illness. So I work for both Environmental Defense Fund and OpenET Inc. as a program specialist. Thank you all for coming. I'm really excited about our session here. I think we have a super panel. So today we're going to learn about how OpenET is being used in various hydrologic systems at different scales, from fields to aquifers, to wetlands, to valley bottoms, and entire watersheds. All of our speakers have applied OpenET in very unique and innovative ways that have no doubt led to improved understanding of these systems, and in some cases have been integral to decision-making at various scales. So without further ado, I'm going to introduce our first speaker, Dr. Gabriel Senay. He's not only a very integral part of our OpenET science team, he leads the CBOP modeling team. He's also a researcher with the USGS survey, or the USGS Earth Resources Observation and Science Center. He conducts applied research on water use and availability assessment and monitoring using satellite data and hydrologic modeling.
Thank you very much, Garsha. Welcome after lunch. Man, it has been a long time since I gave a presentation, so I'm being a little bit nervous. But it's nice to see quite a full crowd in here. So I will be talking about how we apply remote sensing ET, especially on the High Plains Aquifer. So it's really an application, and the model, I guess you'll see that one of the models has been part of the OpenET. I'd like to acknowledge co-authors, a lot of my teammates, Lei G, Mac Fredericks, and Gabe Perch. They were acknowledged earlier as well, part of the CBOP team. Gabe is probably here. So, and also some more collaborators. A lot of slides I'm going to show you, provided by some people in here. Especially I want to acknowledge Desert DRI Research Institute, Charles Morton, and Justin Huntington as well. All right, so this is what I'm going to talk about, why we are doing this. It's USGS does water census. It's just part of that. The whole ET modeling using remote sensing is based on that. I'm going to talk about blue water, green water. It has been mentioned earlier as well on that, part of the effective precipitation. So focus on the High Plains Aquifer, and I'm going to show you how our data from remote sensing ET compares to withdrawal data, like how much water was applied in part of the High Plains Aquifer, and some assessment already John Vogt talked about earlier, how good are the models. So motivation, this is why we do it. USGS has a mandate to do, just assess water use in the US. It's done every 5 years. So now the question, can we do this every year using remote sensing with a more consistent method? You can imagine doing this for the whole US, involves a lot of people across many states. Can we do this with remote sensing? That's the whole point. And this, there's a nice quotation from National Research Council. These water use reports are one of the most highly cited with US Geological Survey publications. And these are published since the 1950s, every 5 years. It takes 5 years really to compile. This is a very expensive process, a very laborious process. So to start out with the focus of my presentation, High Plains Aquifer, this is one of the USGS cover pages in one of the reports. As you can see, we all know this. Let's see if this works. So, what you see in red is the groundwater depletion. And the numbers may not show very well. It's like 150 feet. These are fossil water. Water has been in the ground for many thousands of years and has been extracted, and this shows. Now I'm going to talk about is why is this happening? So it's because of really a lot of irrigation. And can we capture that with remote sensing methods? Just briefly, what goes into what I'm going to show you? Well, it's a lot of modeling and satellite data. So we're going to use two models. One is CBAB, this is an OpenET model, and a water balance model. And we use Landsat data. For weather data, we use GridMet, with irrigated land data from Land ID. It's called Landsat-based irrigation data sets, a great data sets. It's available. LC map from USGS EROS, and water use data, reported data as well, withdrawal data. So what I'm showing you is how we compare remote sensing-based data with reported data. And computing platforms, we use OpenET, Google Cloud GE, Google Earth Engine cloud computing platform, and also another model in Amazon Web Service. All right, blue water, green water, effective precipitation by Connor. So that's the whole point. What's green water, blue water? Rainfall, precipitation, when it hits the land, it takes two pathways. So this is a definition by FAO. It's more or less a more recent concept in 1995. So part of it will goes to unsaturated zone in the soil. So that is called green water because it makes the landscape green. I think that's why they call it green water. So what's blue water? Blue water is the part of precipitation that joins the rivers and the groundwater. So it's a more manageable, so more kind of an expensive water. So what we see is, and when plants evapotranspire, some of it could come from green water, or some of it could come from blue water, from more expensive water. So our goal is actually, we want to know how much of it's really coming from blue water. That's a managed and more expensive water. All right. So when you look at that, who is blue water, who's green water or blue water in the U.S.? Well, a lot of the West, a lot of irrigation like Palo Verde, Central Valley, there's a lot of it's blue water. It's just from groundwater, from surface water. That's easy. And in South Dakota, a lot of the Midwest is green water, rain-fed system. Some pasture in Kansas, in eastern Kansas, provide rainwater. Now, what happens is when you have supplemental irrigation, a lot of central U.S. and eastern U.S. is a mix of irrigation, and so blue water and green water. So the most difficult part is really when you have this mixture, we want to separate how much is really coming from blue water. Something like this. Okay, you can see that you're irrigating and it's raining. So we're trying to separate this problem, guys. It's not an easy problem. So that's the whole point. So schematically, this is what we do. So remote sensing ET, like OpenET, gives you this what we call total water, because satellites just look at the land surface temperature, evaporative cooling. It gives you an estimate of 1,000 millimeter, but it doesn't care where the water is coming from. But some of it, like using a water balance model, we say, hey, what? The rainfall contribution is maybe 300 millimeter. That's like effective precipitation that Connor introduced earlier. So the job is, can we differentiate a total ET from OpenET and some kind of water balance ET, and can that difference be the net ET, the irrigation that comes from blue water? So this is an example of a product we produce through the OpenET system of CBAB for the US. This is, for example, a 5-year average. If you take 10 years or 3 years, it's going to look the same. The most important is where I have circled for you in red. And a lot of you are familiar with, these are heavily irrigated regions of the US, where you see a lot of ET, like in the Snake and the Columbia Plateau and Central Valley, right? So now I'm going to contrast this with this. This is when you run a water balance model that's driven by just rainfall. This is an example for one particular year. Higher ET in here, of course, a lot of rainfall or a lot of vegetation, right? But what happens to those areas? Well, there is not much ET because this is really driven by rainfall. So if there is no rainfall, you don't expect ET. So what are we trying to do? Well, the difference between what I showed you in here, higher ET in those irrigated areas, minus this driven by rainfall, the difference should be irrigation ET. That's the whole point. Now I'm going to show an example in the high plains aquifers how we are applying this. So why the high plains aquifer? Well, a lot of you are familiar with what's happening with Ogallala. So this is 42% of the region is cropland, and out of that, 41% is irrigated land. So as you can see in here, a lot of this color, cropland in yellow, I don't know how much you see it, maybe orange color, and the greenish color is where there is irrigation, and part of Nebraska and southwest Kansas and the panhandle of Texas. That's where a lot of the irrigation is. So, but I want to show you something, what's hydroclimatology of the region. If you look at the Ogallala Aquifer, what's happening? So we're looking at data from 85 to 2020. We look at precipitation, what's happening in precipitation? Well, actually, there is an increase. This is just a trend I'm showing you. There is an increase in precipitation in the upper part of the basin. But what happened in here is a decrease in precipitation. And that's where really the groundwater, the groundwater was, oh, maybe I went too far out. If you, boy, yeah, if you remember this, that's where the groundwater is depleted. And that's the region where precipitation is also going down. Now, fast forward. And what happens in terms of temperature? Again, the same region, the temperature has been increasing. And what happened with the reference city? Atmospheric demand, which means has been hotter and drier, less humid. So really all the regions we're concerned about is actually the driving factors are being compounded. So that's the region. And in terms of withdrawal, so how is this area being irrigated? Well, you can guess in here actually 87%, this particular year, but it's going to be close to that. 87% of the irrigation is from groundwater. Only 13%, and most of it's probably in the northwestern part of the basin from rainfall, from surface water, like, from the Platte River Basin. And in terms of irrigation area, these are the irrigated area in Nebraska and all these known areas. So this is the background, what's going on. So now we're looking at data supplied by USGS every 5 years, remember? USGS compiles data every 5 years. And this is in depth units, and this is by county. So that's advantage of remote sensing is also the high spatial resolution. USGS has been compiling just one value for the whole county. So, and these are every 5 years, what it looks like in depth. So now I'm going to contrast this, what you can get when you do remote sensing based. As you can see, there is a much more spatial detail, and areas of, remember the irrigated areas in Nebraska and Kansas, that's a higher value. This is 20 inches, higher irrigated blue water, ET, you see in those irrigated areas. And we have now 2020, but actually the 2020 compilation by USGS is not ready yet. So just to get for you a closer look, a fine detail in just selected areas in here, this is in Nebraska and Kansas, and just, you can see fine detail with remote sensing. I think a lot of you are by now you're sold. Remote sensing, it gives you a lot of detail, and that's what you're getting that you don't get from a county-based assessment. And so I'm gonna zoom into Kansas, part of the High Plains Aquifer, because we have a lot of yearly data, ground observed data. So this is the kind of data we're getting from Kansas Department of Agriculture, withdrawal data by irrigated areas, and we aggregated this just for this presentation for the whole region. And we're comparing it to ET based on remote sensing from OpenET based. So what you see in here, I think probably the middle is more telling. So this what you see is just the water depths and the blue water depths. And this is the one from withdrawal, how much they pumped from the ground. So as I said, most of it from groundwater, right? So you can think of it, this is pumpage from the ground in red and black, and open circles from ET. And you can see how it's really catching the temporal variability. So remote sensing captures really temporal variability. Even if we have question on the absolute magnitude, at least we are tracking the temporal variability very well. And this is just a scatter plots in here. So now, what's the difference between the magnitude in here? Well, that's withdrawal. So which means not all the water that's withdrawn will be used by the plant. So the difference could be attributed to what? To irrigation efficiency or other kind of errors. But most of it's probably irrigation efficiency differences. So this is just in volumetric, so the depth, each one of them would work. So this just includes the area, but this is just volume per unit area. So, see. So actually, I have some little animation for you. Am I running out of time? How much time? Done?
About 3 minutes.
3 minutes? Okay, I can do that. So this is just a nice animation. On the left, you can see pixel-wise change over time, and as you go in just different years. We're using here from 1997 because the land ID data irrigated area map starts from 1997. But potentially, we can go back to 1985 when we improve our irrigated area estimation. But whoever provided land ID, they only went back to 1997. All right. All right, see if I could go to the next one. So what we did is that was for Kansas because we had yearly data from Kansas Department of Agriculture. For the whole region, we don't have yearly data. But you can see we did just the whole croplands, and you can see the same. So what's interesting here is there was some kind of increase in blue water ET, and then after 2000, it kind of leveled off. But and another thing to note is like drier years, like 2012, there is more withdrawal data, more ET as well, probably for two reasons. One is there is a lot more atmospheric demand, and the plants are pumping a lot more just ET. That's one of the reasons. Maybe also there's intensification of irrigation because really there is not much rainfall. When there is not much rainfall, you have to pump more to compensate for that. So just a combination of the two you can see in drier years. And the nice thing is just remote sensing based DT captures that. So I think I'm running out of time. Oh, well, again. And you see the black lines are just really especially when it's one Landsat, we're missing imagery. So whoever talks to Congress, more land satellites. Whenever we have two satellites, we're good. When we had only a Landsat 5, there were more data gaps. We require at least one image per month to create these seasonal totals. All right. Okay, there is no time for background. You all know about how we do this modeling. So just we'll go to, and John already showed how this model compares this CBOB, this ensemble. Ensemble definitely is better in handling random errors. It's average of 2, but if you only choose one of the models, it is still good, but not necessarily as good as ensemble. So it's always about the users to choose, which models to apply where. So summary remarks, again, spatial temporal variability of irrigation water withdrawal is strongly correlated and explained by remote sensing. It is really, that's good news. And if you just are in a hurry, we can go back down at the end. If we want to improve the really absolute accuracy of remote sensing ET, what we need to do is really bias correction. So remote sensing ET is very good in capturing spatial and temporal variability. Bias can be removed with some reference observed data. With that, I thank you, and I finish, and I'll pass it back to you. All right.